This lesson deals with line and phase relationships. You can find these notes in the ECE202 ebook in chapter 16, starting on page 25. In our last video, we showed some relationships between line voltages and phase voltages. In particular here, V sub AB was equal to V sub AN minus V sub BN. But V sub AN had a magnitude of V sub P at angle 0, and V sub BN had a magnitude of V sub P at angle minus 120. Now let's put these into rectangular form because we're going to subtract them. So 0 degrees is going to be 1 plus J0, and then minus 120, let me try to calculate this a little different way than using your calculator. The cosine of 60 is 1/2, and the sine of 60 is the square root of 3 over 2. The cosine of 30 is the square root of 3 over 2, and the sine of 30 is 1/2. Okay, minus 120 degrees is in the third quadrant, and we're 60 degrees away from 180 degrees. So we take the cosine of 60 and the sine of 60, we would get 1/2 and square root of 3 over 2, but we're in the third quadrant, so the real part and the imaginary part are both negative. Okay, we can pull out a V sub P now, and I've got 1 plus 1/2, that's 3/2, and then I've got 0 plus J square root of 3 over 2. Now think of this as the square root of 3 multiplied by itself. So we're square root of 3 times square root of 3. So I can pull one of those out, and I'm left with the square root of 3 over 2, and then it's 1/2. It looks like our formula down here, that I've got the square root of 3 over 2 and 1/2, and that would be the cosine of 30 and the sine of 30. So that'd be my angle at 30 degrees. So our resulting magnitude is the square root of 3 times our phase magnitude, and the angle is 30 degrees. We can do the same for the other line voltages. So V sub BC, we showed there was V sub BN minus V sub CN. V sub BN was V sub P at angle minus 120, and V sub CN was V sub P at angle minus 240. Now we just showed that this was minus 1/2 minus J square root of 3 over 2 and put it into rectangular form. Now what about 240? Well, it's a negative 240, so we're going to be in the second quadrant. We'll be 60 degrees away from 180 degrees. So again, if we take the sine and cosine of 60 and then adjust the sines to put us in the second quadrant. So here's the cosine of 60 and the sine of 60, so 1/2 and square root of 3 over 2. But if we're in the second quadrant, the real part is negative and the imaginary part is positive. There's a way to express this in a non-decimal way. Okay, now subtract these two. So I have 1/2 minus a minus 1/2, so I get 0. And then I've got this term minus this term, so I've got that twice. So 1/2 and 1/2 square root of 3 just gives me square root of 3. The magnitude of this is the square root of 3, so times V sub P, and then the angle is just minus 90. So the line voltage, V sub BC, is the square root of 3 times the phase voltage at an angle of minus 90. And one last one, V sub CA, we show was V sub CN minus V sub AN, magnitude of V sub P, angle of minus 240, and this was V sub P at angle 0. Now we just had shown that this was minus 1/2 plus J square root of 3 over 2, and this of course is just 1 plus J0. Pull out a common V sub P in the subtraction, and then I've got minus 1/2 minus 1, which would be minus 2 over 2, so minus 3/2, and then I've got just this term minus 0, so it's going to be the square root of 3 over 2. So let's pull out, again, a square root of 3 here, and what I've got left over then would be a square root of 3 over 2, and then pull that square root of 3 out over here. I'm left with a 1/2. This looks like our sine and cosine of 30 degrees from the last page. Here would be the cosine of 30, and here's the sine of 30. Now we're actually in the second quadrant, because the real part's negative and the imaginary part's positive. So that would be our 30 degrees from the 180 line. So that'd be a minus 210 degrees. So the magnitude of our last line voltage from C to A is the square root of 3 times the phase voltage, and the angle is minus 210 degrees. Now let's just sketch these out in our complex plane. Here's our phasors for phase voltages, AN, BN, and CN. And if we sketch these results here we just found, V sub AB was a little bit longer, it was a square root of 3 longer than this one, and the angle was 30 degrees. V sub BC was actually at minus 90, but again square root of 3 longer than our V sub BN. And our last one is same thing, longer, but the phase angle is equal to minus 210. So instead of minus 240, you got minus 210. So these line voltages are likewise shifted by 120 degrees. Their lengths are the square root of 3 longer than the phase voltages. And they also form a vector sum that's equal to 0. Lastly, I wanted to show that you get the same results by doing some vector algebra. As we had shown on page 23, the voltage V sub AB is equal to V sub AN minus V sub BN. Okay, well here's V sub AN, here's V sub BN. If we take the negative of it, it would be just 180 degrees of phase shift, same magnitude, just shifting the angle. And then the vector sum of these two would be equal to this. Just translating this vector over here. Just adding up these two, you get this as a result. Do the same thing for v sub bc. That was equal to v sub bn minus v sub cn. We take the negative of this and then add these two vectors together. Just translate this over here. So this plus this would be equal to this. And lastly, v sub ca is equal to v sub cn minus v sub an. So we take the negative of v sub an. That would be over here. And then just translate this up to here. And then add these two vectors and you get v sub ca. And these are some line and phase relationships.